Light. People have been trying to understand light for as long as people have been able to ask the question, what is light? And for as long as people have been asking that question, well, then they tried to answer the question by coming up with a variety of experiments to do so. Why would we bother talking so much about this that it has its very own PowerPoint show? Because light is incredibly important to astronomy for a couple of reasons. First of all, we can't go to most of the other places we study in astronomy. We can't travel to the next galaxy over and pick stuff up and take it back to the lab and check it. And yet if you open a textbook, you'll find out how far away the Andromeda galaxy is, how fast it's spinning, even what elements it's composed of. Well, how do we get all of that information if we can't actually go there? We get it from light. Light carries information, and that information is so important to us in astronomy that we spend a lot of time trying to understand light. The basic nature of light was an enigma for centuries. Basically, everybody was trying to figure out what light was, and people were coming up with experiments, and the experiments were giving different answers. Somebody may spend their entire life coming up with the perfect be-all, end-all experiment to figure out what light was and find out that light was a wave. And then they'd tell their friend, and their friend was working on their own experiment. And their friend did the experiment and found no, light was a particle. And then they'd argue about it. And this was happening over and over again. There was this debate over what the nature of light was. Was it a wave? Was it a particle? And this debate continued for about 200 years, with each side having its own experimental proof and its own theories. Well, how can you get two such different answers to the same question? That really is a puzzle. Well, maybe one side had smarter people than the other. Well, actually, both sides had very smart individuals. Isaac Newton fell on the particle side of the debate. Christian Huygens fell on the wave side of the debate. And Einstein? Well, Einstein fell on both sides of the debate. In relativity, he said that light was a wave, and in his photoelectric effect, he said that light was a particle. So, brilliant people on both sides. Both sides had wonderful experiments, so then the question becomes, well, how do we put these two ideas together? Let's start by talking about a wave. A wave is a traveling disturbance that transmits energy with no net movement of matter. What does that really mean? Think of an ocean wave. An ocean wave is a traveling disturbance. It moves through the water toward the shore. It does transmit energy. If you've ever been hit by one, you know a lot about the kind of energy it's transmitting. And it does have no net movement of matter. If you were out beyond the breakers and there was nothing else going on, no undertow or currents or sharks nibbling at your toes, then what you'd find is that each and every molecule of water, and, well, you included, as the wave goes by, would go up and then down and actually make a very slight oval. But you'd come right back to where you started after the wave had moved past. No net movement of matter means that if you add up all the movement, at the very end you're left right where you started. For those of you who like physics, this means zero displacement. A little bit about terminology. Amplitude is how high up or how low down the wave goes from its midline, from its undisturbed state. A crest is the highest point of the wave. A trough is the lowest point of the wave. And a wavelength is the distance between either crests or troughs. You'll notice on this image that there is a lowercase Greek letter lambda next to the word wavelength. This is how we usually designate wavelength, as a lowercase lambda. Another term we need to use is frequency. Frequency is how many wavelengths go by per unit time. and that unit of time can change. If you were watching water waves in the ocean, you might talk about the frequency in terms of how many waves go by per hour. With other waves, for example, talking about light, we might talk about how many go by per second. So when we talk about frequency, it's how many go by per unit time. Frequency and wavelength are related to each other. In fact, they're inversely related. Perhaps you can imagine a slinky. If somebody takes a slinky or even a long rope, they can have a friend hold one end of it and they hold the other. And let's say that they wave that rope up and down continuously, sending a wave form along the rope toward their friend. The faster they do their waving of the rope, the smaller the wavelengths are. So the higher the frequency, the smaller the wavelength. Similarly, they could go the other direction and do these things more slowly, a lower frequency, and you find the wavelengths get longer. Feel free to try this at home. Here we have images of slinkies, and you can see the idea of moving a slinky up and down in that top image. When we talk about waves, all waves have a vibration, or you can call it an oscillation. Either term is correct. A vibration is, in the case of that top picture, that up and down movement. All waves also have a motion from their starting point toward, well, wherever it is they're headed. In the case of that top picture, the origin of the wave is the person's hand, and it's headed toward the wall. Notice in this case that the direction of motion of the wave from the hand toward the wall is perpendicular to the vibration of the wave. Perpendicular means at a 90-degree angle. That vibration is up and down, and the direction of wave motion is left to right. Anytime you have a wave whose vibrations are perpendicular to wave motion, you have what's called a transverse wave. A good example of this might be an ocean wave. The vibrations are up and down, but the direction of wave travel is toward the shore. The bottom image shows a longitudinal wave. This is what happens when vibrations are parallel to wave motion. In this case, the direction of wave motion is also from left to right, from the hand toward the wall, but the areas of compression are your vibrations, and they move along in the same direction as wave motion. Because it travels in little compressed areas, it's sometimes called a pressure wave, but it's more technically called a longitudinal wave. A good example of a longitudinal wave is sound. Sound travels from my mouth through the air in little areas of air where the air molecules are more compact, and then they run into somebody who's listening, the tympanic membrane in the ear. That tympanic membrane vibrates, and somehow the brain makes sense of that. So this is a longitudinal wave. All waves involve oscillation or vibration of some kind. It's very difficult to think of a wave that doesn't have a medium. No, not a psychic, but a substance through which the wave moves. Go ahead and try to imagine an ocean wave with no ocean. Difficult, isn't it? So we normally think in terms of a medium, something that wave moves through. An ocean wave needs an ocean. Your voice, if you're going to talk to someone, also needs the sound needs a medium to travel through. In most cases, air. However, chances are you've been underwater at some point and still heard sound. Sound can travel through water as well. What happens when a wave changes medium? For example, sound going from air to water. When a wave hits a new medium, a couple of things can happen. It can bounce off that medium, in which case it's called reflection. think of a mirror. You're used to reflection. Or it can travel into the new medium, and it usually changes direction when that happens. This is called refraction. For example, when a light goes into a prism or a glass, it changes direction, and it changes again when it emerges. It goes from air to glass to air again. You may have seen something like this in seeing a pencil behind half a glass of water. The pencil looks disconnected. Here you see the refraction of a polar bear. It looks like the poor bear's upper body is disconnected from the rest of him. Don't worry, no bears were harmed in the filming of this. Refraction is most commonly seen in light, in the making of a rainbow. In this case, you can see that all the colors of light, which you would see as white light, come into the prism. Now, each color of light reacts a little bit differently in the prism. Red light bends very little, while blue light bends a lot, and all the other colors in between. So by the time it comes out the other side of the prism, you'll find that the red light almost traveled straight through. Yes, it's bent a little bit, it's refracted a little bit, but the blue light is obviously refracted quite a bit, and those colors of light have spread out to make a rainbow. The numbers next to the rainbow are the wavelengths of light. You can see 700 nanometers up at the red end and 400 nanometers down at the blue end. So you can tell that each color of light has a different wavelength, unique to that color. The longest wavelength is at the red end. The shortest wavelength is at the blue end. Which end has more energy? Well, actually, if you go back to thinking about those slinkies again, if you were to make a short wavelength, high frequency wave, jiggling that rope or that slinky very, very quickly, you'll find that it takes a lot more energy to do that than to make one of those long wavelength, lower frequency waves. Well, just keep that in mind, because making those high frequency, short wavelength waves does take, in fact, a lot of energy. So try to remember high frequency, small wavelength equals high energy. Or the opposite, low frequency, big wavelength equals lower energy. So the high energy side of this is at the blue end. Those short wavelengths for the blue give it a higher energy. So which travels faster, the red light or the blue light? Well, that's kind of a trick question, because they're both traveling at the speed of light. Now, a wave can change speed when it changes medium, similar to if you were walking along the floor, a nice tiled floor, and then walked into knee-deep mud, you would change speed. Similarly, when you change medium, you can change speed. Now, that can be speeding up or slowing down, depending on how you're changing medium. Sound travels more quickly in iron than it does in air, and this was used quite a bit in the Old West. If you couldn't see or hear the train coming, you could put your ear to the railroad track and hear it along the rail long before you could hear it standing next to the station. Please never ever put your head on a railroad track.
In the mid to late 1800s, some very bright men noticed a similarity between electromagnetic studies and light as a wave studies. Some of these brilliant men were James Clerk Maxwell, Faraday, Hertz, not the rental car. But they looked at what was being done and said, wow, this looks a whole lot like what we've already done while studying electromagnetics. Well, once somebody suggests it, somebody's got to test it. And so the idea came up to compare the speed of light as measured by people studying light versus the speed of light as calculated using Maxwell's equations, which were made based entirely on electromagnetic studies. These were successfully compared, and it gave us a whole new idea of what light might be. This is seen as one of the greatest intellectual achievements of all time, connecting light with electromagnetism. This is a t-shirt. Uh, these are Maxwell's equations that govern light. So when thinking about light as a wave, the idea came up, well, what is the medium for this wave? So now the search for the medium for light was on, and instead of saying the medium for light, they gave it a name, the ether. Well, experiment after experiment after experiment was done trying to find the ether, and experiment after experiment after experiment failed. And after each failure, somebody pointed out, oh, but you missed this one little thing. And the experimenters go, oh, you're right, I did. And another experiment was done where that was taken into account. And then that one failed, and somebody pointed out, oh, you missed this little thing. Oh, you're right. And we tried again and again and again. So the experiments got more and more complex and took more and more things into account until we got to the Michelson-Morley experiment of 1887. Now, this was a very complex experiment to look for the ether, but the concept behind it wasn't that complex. The idea was you're looking for a medium when you can't see it. So imagine you could see an ocean wave, but you couldn't see the ocean. I know that's a difficult one to imagine. But the idea was you would be able to tell that the ocean or the ether was there because whatever was going on in that medium would affect the waves. And so if we saw an effect in the waves, we'd be able to determine that the medium was there. So they were looking for the equivalent of, say, currents in the ocean. Currents in the ocean will affect the waves above them. They're looking for currents or wind or however you'd like to think about it in the ether. So they took in incoming light and they had it pulse. So you can imagine it getting brighter, dimmer, brighter, dimmer, brighter, dimmer. And it came in, as you can see from the left side of this image, and it hit a beam splitter, which did exactly what a beam splitter is supposed to do, and split the beam. Half of that beam split upward toward the mirror, and the other half went through the beam splitter to the mirror on the far side. It was very important that these distances were exactly the same. You wanted travel time to be equal. Then they hit the mirror, came back to the beam splitter. The one from the top goes straight through the beam splitter and down, and the one from the right-hand mirror makes a 90-degree turn and also goes down into what they called the telescope and what you would now call a detector. The idea is if there was a current or a wind in the ether, well then the light wave could be sped up or slowed down, and so when the two beams came back together, the pulses would no longer be lined up. Instead of both of them going brighter, dimmer, brighter, dimmer, brighter, dimmer at the same time, you might have one going brighter, dimmer, and the other off. So you'd get brighter, 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 back and forth. And that's what they were looking for, those two beams no longer to be in sync. Well, once they thought they got everything set up and everything thought of, in 1887 they ran the experiment and there was no difference detected between the two beams. A null result. Now, some people would consider this a failure, but it really wasn't. This was the experiment to end all experiments in searching for the ether, and if it couldn't find the ether, then maybe we needed to reconsider what the ether was. So this made everyone take a step back and really think about what they were looking for and to consider maybe they were looking for the wrong thing and they needed to rethink the whole idea. Little bit of trivia here. Michelson was the first American physicist to win the Nobel Prize. So if there was no ether, then what was needed? Well, the answer came from Albert Einstein in his 1905 special theory of relativity. We're not sure how much of a role the Michelson-Morley experiment played in his decisions or his writings, although we do know that he was aware of them. But in his publication, Albert Einstein stated, "The introduction of a light ether will prove to be superfluous." Superfluous means that it was unnecessary because it was too much. He really thought there was a simpler explanation. His explanation was electromagnetic waves. The idea here is that a moving electric field will make a moving magnetic field, will make an electric field, will make a magnetic field, will make an electric field, will make a magnetic field, and on and on and on. He said you didn't need a medium because light is electromagnetic, and as soon as it gets going, these vibrations will keep it going, and therefore it could travel without a medium through empty space. It was quite a revolutionary idea, a wave without a medium. So at this point then, light is thought of as an electromagnetic disturbance with wave properties that's self-sustaining, able to carry itself through a perfect vacuum, but there were still problems with this whole idea. Light as a wave might explain how light can bend around a doorway, so that if you're in a darkened room with a light on in the hallway, the light bends around the door and slightly brightens the edge of the back of the door. However, it will not explain eyesight or photography. So we do need another way of going. Enter Max Planck, and that is how you say his name, Planck. He is one of your fathers of quantum physics, and he was the person who is going to help bring the ideas of light as a particle and light as a wave together. He also won a Nobel Prize. So what did Max Planck do that was so amazing? He was trying to figure out the connection between the color of light emitted from a hot solid and the temperature of that hot solid, because it had already been noted that as you heated up a solid, at first it starts to glow red, and then as it gets hotter it starts to glow a kind of yellow, and then a yellow white, and if you can get it hotter still, you might even get it a blue white. So he did come up with a formula that agreed very closely with the experimental data, and it was a very simple formula that would allow you to look at the wavelength of the color that's being emitted, and you could put that into the formula and that would give you the temperature. Or you could put the temperature in and that would give you the wavelength of the color that you are going to see. And it worked beautifully. The thing was, that whole model was based on one large assumption. It was the assumption that the energy of a vibrating molecule was quantized. That means that the energy could have a specific value. Think stair steps. It could have the lowest value or the next or the next or the next, like standing on stairs. What it could not have is something like a ramp. It could not have any energy along that ramp. It could only have very specific ones. And people said, well, why couldn't it have just any amount, any sliding scale amount? And he said, I don't know, but as soon as you assume it's quantized, everything works. Niels Bohr is going to be able to explain why this happens, and he too will win a Nobel Prize for it. So, is it a wave or is it a particle? The amount of energy a photon carried is based on its wave properties. And if you look at this picture here, this does appear to be a wave. Now imagine it extends in both directions beyond the picture, and as it goes further out, the amplitude gets smaller and smaller until it flatlines in either direction. You'll note you can only see the wave right there in the middle where it's got amplitude. But that doesn't mean the wave doesn't exist elsewhere. But if you can only see it in one place, if it only has amplitude in one small area, that's the only place you see it. And even if it's got tails in both directions, if you only see it in one place, it's going to look like a particle. So this brought together the idea of a wave and a particle. A particle is a wave, and a wave is a particle. Well, as soon as somebody said that, of course you knew it had to be tested as well. And somebody said, oh, well, how about an electron? Everybody knows an electron is a particle. So they devised an experiment to see if it ever acted like a wave. And guess what? In the right experiment, an electron can act just like a wave. So this is one of the bases of quantum physics. A particle is a wave, is a particle, is a wave. Based on Planck's work, Einstein proposed that light also was quantized and delivered energy in small amounts. Again, not a sliding scale. You can't have any amount, but specific amounts. And the amount of energy that this particle of light would carry would be based on its wave characteristics. Now, a particle of light became known as a photon, and the symbol for a photon was actually a mixture of the symbol for a wave, which is just a wavy line, and the symbol for a particle, which is an arrow. So the symbol for a photon is a wavy line with an arrow at the end. So our modern concept of light says that both Newton and Huygens were correct. We have three fundamental elements to this concept. First is duality. Light can act either as a stream of particles or it can act as a self-sustaining wave depending on the circumstance. Complementarity. The wave and particle properties of light are mutually exclusive. What that means is that in any given experiment, you will find that light acts like a wave or light acts like a particle. You will never find an experiment that shows both, or at least we never have in all our years of trying. Convertibility. At this point, the distinction between energy, light, and matter is gone. You can think of light as pure radiant energy. You can think of matter as energy. It's all the same thing. Now, this is non-intuitive to us because we're not used to thinking of matter like a table turning into light, beaming itself somewhere, and turning back into matter again. However, at high enough energies, things like this can happen. And this is the idea behind Star Trek's transporter beam.